Okay, here we're going to use a reaction mechanism. We're just going to take this reaction and assume the reaction mechanism for it is known. And we're going to use that to predict the reaction rate given changes to concentration. So here's our reaction mechanism. We have 2a plus b squared going to 2ab, and the rate limiting step, or the slow step, is going to be 2a becomes a2. So this is really the only step we're interested in. These are fast. What we assume is they go so fast that they don't affect how long the reaction takes. So we're focused on that guy. Now we know then that our rate is going to be proportional to this part of the reactants. So that would be the concentration of A. And because it has a 2, we say the concentration of A squared. So what that means then is I can set up ratios using that proportionality to see how changing A will affect the concentration. So if I have my new rate, which I'll call rate 2, and I want to compare that to rate 1, when I set up these ratios, if I put the thing that I'm looking for on my upper left, it makes my life a little easier. And here I can see that rate is proportional to the concentration of A squared. So I'm going to put the concentration of A 2, or final, up here, squared, divided by the concentration of A initial squared down here. So let's change that. Instead of 2 and 1, let's use initial and final. It occurred to me when I was going to do that if I had used 2 there, it was going to look like A2 instead of just A, and that was going to be a little confusing. So I'll use final and initial. So I want to know what my final rate is, or what my rate is going to be with the changed concentration. My initial rate is 0.1. I took that from right here. And I can see that my final, so I'm predicting for this spot right here, my final is 0.3 molar squared because of the rate law, divided by my initial, 0.15 molar squared so my rate in my final situation, if I do 0.3 squared divided by 0.15 squared, I'm going to end up with 4. So my rate in my final situation is going to be 0.4 molar. So that's that one. Actually, I shouldn't put that there because I have it in the heading, so I shouldn't put that there. Okay. If I change I'm still an eraser. Sorry about that. If I change the concentration of B, leaving the concentration of A the same, since the rate limiting step doesn't depend on B in any way, there's no dependence on B in the rate law, which means changing B will have no effect on the rate of reaction. So this one's easy. I can just put 0.1 down here. There's no B, no B2, so no dependence. And one more here. Here I'm going to change A and B based on what I just discussed. I don't care about the fact that I changed B, so I'm going to ignore that change, and I'm going to focus on my change in A, setting up my ratio again. So here again, my rate in my final situation in comparison to my rate in my initial situation. I can set up a ratio based on the rate law. Concentration of A final squared divided by the concentration of A initial squared. So here my rate in my final situation is going to be equal to 0.4. Or not 0. Sorry, hold on. My rate in my final situation is not equal to 0.4. Sorry, my rate is rate over 0.1, my initial rate. And over here, A final, 0.4 squared divided by 0.15 squared. And I actually have to use a calculator for that one because it's not just doubled. 0.4 squared divided by 0.15 squared. So that works out to 7.11. So my rate in my final situation is going to be 0.711. So, based on your slow reaction step, you can come up with a proportionality between the rate and the concentration of the reactants. You can use that to set up ratios and use that to predict the rate. If a chemical reactant does not appear in the rate limiting step, then there will be no dependence on that concentration of that reactant with regard to the rate of reaction.